There, Mr. Sutton here, bringing you the Algebra 2 8-4 homework solutions on independent and dependent probability. The first few problems on this homework, we're just going to be figuring out if the events described are independent or dependent. So here we have a bag with 4 quarters and a nickel. You randomly pick 2 coins. Determine whether selecting a quarter first and randomly selecting a quarter second are independent events. So they didn't say that we put the money back, so presumably we're pocketing the money after we get it. So then whatever you get that first time is going to affect what you have to choose from the second time around. Since the first chosen coin chooses your possible outcomes for the second coin, we would say these are dependent events. On this problem, we're playing a game with a spinner, and we have the same area for each section. We just spin a few times here. We want to determine if randomly spinning blue and then green are independent events. Well, if I spin blue the first time, that doesn't really change my available options for the second spin. I could still get blue or any of these other colors. Since the first spin doesn't change the outcomes for the second, these are independent. On this one, we have a student taking a multiple choice quiz. Each question has 4 choices. They randomly guess the answers to the 3-question quiz, and we want to know if guessing the correct answer to question 1 and question 2 are independent events. Well, since they're randomly choosing, and whatever I pick on question 1 doesn't change my available choices for question 2, presumably these are going to be independent. So question 1 answer doesn't change outcomes for question 2, so independent. And this is going to be true whether it's a multiple choice or a true-false. Now, if this were a quiz where it was a matching and you only got to choose each match once, that would affect possible outcomes for later questions. On this one, we have 3 green apples and 1 red apple in a bowl, and beautiful picture of that. We randomly select an apple and eat it, and then another apple that we're going to eat with lunch. Does randomly picking a green apple first and randomly selecting a green apple second, are those independent events? Well, you can't have your apple and eat it too. So if you pick a green apple the first time around, then that's 1 less green apple you have to choose from for lunch. So yes, the first apple choice changes your possible outcomes for the second. So these are dependent. For this problem, we have 3 different local hospitals in New York surveying their patients. Surveys asking whether the physician communicated efficiently, and they gave the results as a joint relative frequency table shown below here. We want to know if being satisfied with communication of the physician and living in Saratoga are independent events. So the way we're going to figure this out is we're going to see what the probability of yes is just by itself, and then we're going to look at the conditional probability of yes given that we're living in Saratoga. So for the probability of yes, we just have to add up everybody in the yes row right here. So 0.123, 289, and 0.338. And I'll go to the calculator for that. So 0.123 plus 0.289 plus 0.338, grand total of 0.75. Now we want to know the probability of yes given Saratoga. So for that, we're going to have to figure out the probability of yes and Saratoga, which is just this 0.289. And then we'll need to divide that by the probability of Saratoga in general, which is 0.289 plus 0.095. And let's see what the calculator has to say about that. So let me open a fraction, 0.289, and divide that by 0.289 plus 0.095, grand total of 0.753, which is pretty close to what we got for just the probability of yes. So I think that's close enough to conclude that these are independent of each other. For this problem, we have a bag with 12 movie tickets and 8 concert tickets. We randomly choose a ticket and don't replace it. Then we pick another one. We want to find the probability that the first ticket is a concert ticket and the second ticket is a concert ticket. Well, since I'm not putting the ticket back, my first draw is going to affect the sample space, the options for that second draw. So these are dependent, and we're going to use our dependent formula. So P of A times P of B given A, not just simple P of B. So let's find each of these components individually. So P of A is just probability of getting a first ticket that's a concert ticket. There's 8 concert tickets, and there's 8 plus 12, so 20 overall tickets to choose from. So 8 over 20, which we could reduce if we wanted to 4 over 10 or 2 over 5. Now let's find P given A. So we're looking for a second concert ticket. We already got one. So that means out of those 8, there are 7 left, and there's 19 overall tickets to choose from. And we can't really reduce that at all. So multiplying these together, 2/5 times 7/19, that's going to be 14 over, I believe, 95, which can't be reduced, so that's as good as it gets. For this one, we're playing a game that involves spinning a money wheel. It's kind of like Wheel of Fortune, where they're telling us there's 24 equally sized areas, as shown. I'm glad they told us. I didn't feel like counting. We spin the wheel twice. We want to find the probability that we get more than 500 on the first spin, and then go bankrupt on the second spin. Well, nothing is going to get removed from the wheel, regardless of what we spin the first time. So these are independent. One does not affect the other. Let's find the probability of getting more than 500 on the first spin. And before we do that, just to kind of map out where we're going with this, we're going to be using our independent probability formula, P of A times P of B. And let's let A be the more than 500 event, and B will be bankrupt, which kind of works out. B for bankrupt. All right, so let's find more than 500. Let's just start at this bankrupt and start going around. So we'll just count them up. We've got 1, 2, 3. That's 250. This looks like 950, so that's 4, 5. More than 500, so that doesn't count. So we're up to 6, 7, and 550 counts, so 8. So that is 8 out of, they said, 24, which we could reduce to 1 over 3. Now for bankrupt, that's a little bit easier. There's 2 of those. So 2 out of 24, which is 1 out of 12. Just multiplying these together now, we have 1/3 times 1/12, which is 1 over 36. For this problem, we are a DJ at a wedding. We have a playlist with 10 pop songs and 20 country songs, and we're going to pick them at random, of course. Once a song's played, it will not be played again, because people would not be thrilled about that. We want to find the probability that the first 2 songs are country songs. All right, well, since you can't play the same song twice, that means what you play the first time affects what you have to choose from the second time around. So these are dependent events. We're going to use the dependent formula, P of A times P of B given A. And let's say that event A is a country song, and event B is another country song. So probability of A, the first time around, we have 20 country songs, 30 overall, so 20 out of 30, which we can reduce to 2/3. Now the second time around, we've only got 19 country songs, and only 29 songs overall. So that's our conditional probability. Multiplying these together, 2/3 times 19/29, that's going to be 38 over, let's see, 87, which I don't think can be reduced at all, so that's it. On this problem, we're playing a game that involves drawing 2 numbers from a hat. There's 25 pieces of paper, numbered creatively here, 1 through 25. Each number is replaced after it is drawn, so that's the key on this one. We want the probability of drawing a 3 the first time and a number bigger than 10 on the second draw. Well, since we put the number back and we have the same chance both times of drawing all the numbers, that means these are independent events. They might as well just be completely separate events. So we'll use our independent formula, P of A times P of B. Let's let A be drawing a 3 on the first try, and then B is going to be a number that's greater than 10. So probability of drawing a 3 is just 1 out of the 25. Probability of a number bigger than 10, well, we've got 11 through 25. If you're careful counting those, you'll see that's a total of 15 numbers. So 15 over still 25, because we put that initial piece of paper back. And we can reduce that to 3 over 5 if we like. So multiplying these together, we have 1/25 times 3/5. That'll be 3 over 125, which cannot be reduced. So that is all.